Okay. Okay, so welcome again to this probability seminar, and it's a pleasure to have today somebody you should know. We know Avelio, and Avelio is going to speak about the interplay between the Gaussian free field and the spin-ON model.
Yeah, thank you very much, Joaquin, and it's really a pleasure to be here, even though I am here every time that it's something more. But somehow it's my first time being on this side of the room. Actually, yes.
You have to thank the organizer.
Thank you to the amazing organizer of the probability seminar to have chosen me to be able to speak here. So I'm going to discuss about my favorite object, the Gaussian free field, and its relationship with the spin-ON model. So it will be a two-way relationship, both the spin-ON model techniques helping us understand the GFF, and at the same time the GFF helping us understand the spin-ON model. So it's somehow, I'm going to discuss about this thing. It's like a long research project, which we are in the middle of, but there are two papers that have already appeared in this research project. So this I'm going to discuss about, but the main objective will appear in the middle of the talk. So I will try to explain. I need to click here. Yeah. So we are going to start with the context. We are then going to see how understanding the GFF helps us to understand the spin-ON model. Then we are going to go the other way through. And finally, we are going to try to fix three, saying like, okay, the GFF maybe is not the right model. How can we fix the GFF? So these first two are works with Juhan Aru and Christophe Garban. And the last one is with Aleksandra Krozhenkova, which you met 2 years ago or something. She came to visit us, and this is what she did while we were here. We did. So we start discussing spin systems. So spin systems are a random function from the vertex of a graph to something, let's say a group in our case. So the spin systems can take different types of values. They could take values plus minus 1. So it's just like to a vertex, you associate a value plus minus 1. And for those of you who were in the last talk, the AC model already appeared there. So you have this object. It can also take values in the circle, which will be important. It can take values on the sphere of dimension n, or Sn minus 1. Or it can take values in the real numbers. So all of these models are going to share the fact that they are going to be defined using the same energy function. So I'm going to have an energy, which is the Dirichlet energy. So it's the sum of the discrete gradients squared and 1/2, because we are Gaussian, so we like the 1/2. And they are going to be modulated by a parameter which is beta. So I have the energy. And what's the probability of a given configuration, let's say, in all of these models at the same time? So let's think about the Ising model, for example. So the probability of a given configuration is going to be proportional to the exponential of minus beta over 2d energy. And the beta plays the role of playing the interplay between energy and entropy. Okay, so the higher beta is, that means that the temperature is lower, meaning that the energy has more weight. So I'm going to choose configurations that have less energy. And the other way, so if you could take beta equal to 0, for example, you get the uniform measure. If you get beta equal to infinity, you get the uniform measure on minimizers of the energy. So this makes a lot of sense when we are talking about a discrete model. What happens when the spin can take continuous values? Well, when the values are compact, it's somehow the proportional. This is like a Radon-Nikodym derivative with respect to the hard measure, meaning the uniform measure either on the circle or on the sphere. For those of you that do not know what the uniform measure on the sphere is, just take a Gaussian random variable in dimension n and divide it by its norm. It's rotational invariant. Things work out. Then we go to the last friend, which is the Gaussian free field. And in that case, it's in R. So we don't have so this proportional is not with respect to a probability measure, but just with respect to Lebesgue. Okay. And what actually we are going to be also really interested, I'm never going to discuss much about, is that we could discuss about the Gaussian free field, the vector value Gaussian free field. And instead of going to R, we are going to go to Rn. So it's essentially n independent copies, like n dimensional Brownian motion is n independent copies. Yes, and the n value GFF, the vector value GFF is just going to Rn. It's not just n independent copies of a GFF. For the GFF, one needs to be careful because the measure is finite. So you have to put boundary conditions. And whenever we have to choose boundary conditions for the GFF, we are going to put boundary condition 0. Meaning that at the boundary, the GFF, we are going to force its value to be 0. And then we let it run. So what are the main questions in this area? The main questions are trying to understand how the qualitative behavior of the model change as a function of beta. So let me give you so the GFF here, you have a better profile picture. As you can see, in the boundary is 0, and it is the discrete GFF, so I'm not going to discuss about the continuous GFF in this talk. And the way to think about it is, and we are always going to work in dimension 2. So we are always going to, if you have to, we can always fix a graph. Our graph is just a square, yes, contained in Z2. So it's a 2-dimensional square. And you can think about it as a bet. Just every time I'm making my bet, I think about the Gaussian free field. It's like you are doing that. You hit it strongly, and then you take a picture. Okay? And then you have to zoom it in, and you will see that essentially you have springs all the way through, and they are fluctuating because there is heat on top of it. And that's essentially how it works. So what is cool about the Gaussian free field, as also what we saw last talk, is the Gaussian part. The Gaussian part means that we can understand it quite well, because if we come back, this Dirichlet energy is a quadratic form, meaning that the object itself is just a Gaussian vector. So we just need to define its correlations. And the correlation is actually the Green's function, meaning the inverse of the Laplacian. So the graph has a discrete Laplacian. You have an inverse. You have that's the correlation between them. And what happens with the beta? The beta just comes to play the role of the 1 over the variance. So changing beta is just multiplying our GFF by a constant. So it's quite boring, like macroscopically boring. There is no qualitative behavior change if you are just like multiplying things by beta. And we are going to see that the GFF is a special case in this class, because the other one, so up to this point, are there any questions? Is it? I'm always going too fast. So we could start with the Ising model. This is what I was changing at the last moment. I had a simulation by another person, but this I did it recently using ChatGPT. It took me not much. But so, well, here is the Ising model at different temperatures. So so this is, as you can see, so you have two colors. It's either plus or minus 1. Let's say that the plus ones are black and the minus ones are white. As you can see, in this picture to the left, the GFF has chosen to be, the Ising model, sorry, has chosen white as a color. It's mostly white with small patches of black. And this is characteristic of low temperature, meaning beta bigger than the critical temperature. Yes?
No boundary condition here?
So here there is no boundary condition, so here it's a free. So actually it's quite fun. It's called symmetry breaking. Somehow this Ising has to decide if it's going to be either plus or minus. It has to pay. Somehow it's a macroscopic decision that one cannot see. To the right hand side, you can see the typical behavior of an Ising model at high temperature, in which it just looks like a TV which is broke, that black and white TV broken. You are just seeing almost independent black and white stuff. And in the middle, it's the most interesting part, is the critical temperature. It is exactly known in dimension 2, in the square grid. I don't remember. It's like it's a natural logarithm of something. But how? So there is a mathematical way of differentiating them. So low temperature. So this is beta bigger than beta c. One can take a really, really big box, and one can take the expected value of the spin at 0 with the spin at v. And what one will say is that this typically will want to align. Yes, so if this is 1, this one with the right one also would want to be 1. So the limit of this. So I'm taking two limits, but okay, when the norm of v goes to infinity, this is strictly positive. At high temperature, this couldn't be farther away from the truth. If you have beta smaller than beta c, then the 2-point correlation function, so this a really complicated name for this covariance, this limit as norm v goes to 0, goes to infinity, this goes to 0. And exactly at the critical temperature, okay, I'm not intelligent enough, so at the critical temperature, the expected value of sigma 0, sigma v, well, actually it also goes to 0. But there is something tricky, because we see in the drawings that they are qualitatively different, the right-hand side picture with the middle one. So what's going on is that at high temperature, in fact, the convergence to 0 is exponential. And at critical temperature, it's actually not exponential, it's polynomial. This is quite general. However, in the square lattice, we know everything in dimension, actually in dimension 2. So this behaves like a 1 over norm of v. And if I'm not mistaken, is this 1 over 8 or 1 over 4? Well, let's put 1 over 8 now. Yes. Okay. I hope I'm not wrong with the 1 over 8. But it's polynomial. That's the main thing. Okay. And so there is a different behavior, and we understand really quite well the Ising model. There are still many open problems, but it is a well understood model. The next one is the XY model, or the O2 model, meaning that my spin now lives in S1, that's in the circle. So this is a nice way of coloring the angles of the circle. It's called HSV. It's continuous on the circle. So as you can see here is so this is not mine. This is a sampling of an XY model, and one can ask what is going on in this model. Okay, and what one can show is that this model does not have. Okay, with Milan. Okay, just ignore the one on top. I always forget to raise that. But just the Mermin-Wagner theorem tells us that if one wants to study these correlation functions, okay, I was told not to use. This is for XY. Actually, there is never a low temperature regime. This is what this statement tells you, is that the alignment between two spins, it doesn't matter how low the temperature is. There will not be an alignment of the spins. We will have convergence to 0. Okay, so it looks like a boring model. It's like, okay, you have to go either on higher dimensions, so you go to dimension 3. In dimension 3, actually, it has a phase transition, or you keep yourself with the Ising model, because the reason why people are looking at these spin systems is because they want to find phase transitions, because this is what they see in nature.
And this is because you can sort of move.
Yes, this is because of. Okay, so just let me show you one image before the question is answered. So this is the XY model at high temperature and at low temperature. So anyhow, at least they look qualitatively different. And we are going to discuss why this is the case. So let's go to address Daniel's question, why we don't have a phase transition for this. So this is the Mermin-Wagner argument. And the main question is how difficult it is to create a configuration such that all of them are looking to the right on the boundary, and in the center they are looking to the left. Okay, and the main idea is that one can actually construct such a function by taking an appropriate exponential, imaginary exponential of the Green's function, and it is so soft that the energy associated to it actually goes to zero as the box goes to infinity. So in a way, one can think about it like as a Radon-Nikodym derivative of moving the center, multiplying the center by -1. Okay, so that means that actually the law of the center is quite similar to the law of the center of minus the law of the center. So that means that you are almost uniform. That's essentially the main idea. So this is Melvin Wagner's argument. And it has to do with the fact that in dimension 2, you can do it really, really slowly. And this 1 over log actually is 1 over the Green's function at the point x6. So in dimension 3, this argument doesn't work because the Green's function in dimension 3 in the discrete does not explode. But in dimension 2 it does. So it is quite magical. However, there is a more interesting phase transition, or arguably more interesting. Yes?
The dimension 2 is the dimension of the box? Or
the dimension of the box. Yeah. So this argument actually also works for any spin-O n model. Yes, because it's easier. The higher the n, the easier it is to turn around, like slowly. So the things that you have to be able to turn around slowly. So the topological phase transition in this context, it tells you that at low temperature, at high temperature, you still have exponential decay of correlation. So this explains this object. This is what we expect when I say exponential decay of correlation. I want you to think about a broken TV, but now like with more colors. However, what happens in the topological phase transition, and this was conjectured by Bensitsky, Kostelis, and Taulis in the 70s, and shown by this amazing but completely complicated paper of Freud and Spencer, and now redemonstrating by many people who came here last year to have fun with us, starting by a work of Pete Lamers, and well, there was Eisenman, and there's like a seventh named Ron Pellet. Like everyone who was here essentially was playing the game of reproving this statement. But what it tells you is that at low temperature, what you see is like a critical regime, but not like a critical point, but like everything is critical. So it's like someone came, they killed the low temperature regime and replaced it by a critical regime. And this we are still trying to understand quite well how this behaves, what happens close to the criticality, and things like that. So this is the story about the XY.
What do you mean they killed?
It's like you erase this low temperature regime and replace it by a critical. It's like with the Ising model, if you kill this stuff, you get only critical and high temperature. You never get low temperature regime. Like spins never freeze. Actually, it's not frozen. It's alive. Because we will see what it means to be frozen. Frozen is like everyone is almost the same. Like almost everyone is the same. Like a line is, you have a positive like the density of the ones being the same is strictly bigger than 1/2. Then you have in the critical, they don't align, but they somehow want to align a little bit. So you get macroscopically cool images, and the high temperature is just a broken TV. It's almost independent. So what is the big open question? So what happens for the ON model? And arguably, this is the second most important question in maybe in statistical physics, but at least in spin, the study of spin systems, which is Polyakov's conjecture, which tells us that when the n is bigger or equal than 3, meaning that when we already are working on the sphere dimension, the boundary of the sphere in dimension 3 or higher, then you also kill the critical regime. You only have high temperature regime. So you only have exponential decay of correlation. This is called mass gap. That's the name of the physics in the physics literature. And this is related to the most important questions, arguably in statistical physics, which is the Young-Mills mass gap questions, which is essentially also a question of the type a model always is at high temperature. In this case, that model is Young-Mills, and this is the baby, the toy model for that question. We expect everything somehow we have managed to do in dimension 2 for spin system, we have managed to extend for Young-Mills. So everyone is expecting that if a proof is found for Polyakov's conjecture, then this proof will be able to be adapted to understand Young-Mills. And this is one of the Millennium problems, which is the way it's phrased is completely incomprehensible, but we had a course also that year by Malin Palo explaining to us at least what the Young-Mills model is in the lattice. However, this is not an absolutely everyone. Yes.
Understood more from your explanation now.
So Polyakov's conjecture is not believed by every physicist. It's like mostly believed, but there are these amazing works of Patriciello and Seiler where they claim that actually for O3 model one should have a critical. Well, there should be a critical behavior for a temperature low enough. And actually we arrived, I mean, one of the parts of this project started because we had the same idea. We didn't know it at the time. And we had this idea, and I'm going to try to describe to you a little bit what the idea should be. We are going to push, and at a point we realize that our idea breaks at a point. Because we find a nice counterexample. But it feels like it should work. So the first part is we are going to discuss a little bit how one tries to think about this and disprove that their argument, I mean, we show that their argument doesn't work. We don't show that the result doesn't hold. Yes. So in a way, at the same time, it suggests a way of trying to prove this, which we are far from, but I will try to discuss the first steps that we are doing to try to attack this problem. So here is the GFF scaling the spin. So there is a massive version of the GFF in which the energy, instead of being the Dirichlet energy, we also add an L2 term, meaning that the energy of the field is the Dirichlet energy, which is what half the sum of the neighbors phi I minus phi j squares. And I can put a norm here because I can go in higher dimension plus m, the sum of norm of phi I squared. This is a massive thing. And the reason it's called massive is actually, what it means at least is that you will get, your correlations are not going to decrease exponentially by a parameter controlled by this m. The bigger this m is, the quicker you are decreasing exponentially. Or if you want, it's just a spin system with the same energy that we are used to, but in which the base measure is not Lebesgue, but it is a Gaussian at each vertex of mean 0 and variance 1 over m over 2 or something. Yeah. Okay. So the first thing is that spin-ON models are just GFFs. That's an observation that was made for the Ising model by Wendelin and Werner and Lupo. And actually, it's quite easy to generalize, but they didn't do it, so we can claim that we did it. So if you condition, so the main idea is that you can condition, maybe I will not do it, you can condition on the norm of a GFF here. And when you condition on the norm, I had it written down, but I think okay. So when you condition on the norm, just let's see at this term, phi I. So if you condition on the norm, this term doesn't matter because it just depends on the norm. So you're just looking at the difference. And condition on the norm, you have to do phi A, phi j, phi I minus phi j. So this is squares, and you can write this as the angle which actually, if it was a one-dimensional GFF, like a classical GFF, the angle is just a sign, it's either +1 or -1. But if it's a two-component GFF, it is the angle is in S1. You can do times the norm, which we can call psi I. So you have this square, and you can. I will not do the computations, but you can check that this one will give you an energy which is similar, so it's up to a constant, up to constants. This is chi I times chi j. Sum I neighboring j, chi j over 2 sum theta I minus theta j square. Yeah. So you can do the computations, and of course you just care up to constants because you are doing exponential of this and you are taking proportionality. So it's the classical thing in which you just care about only things that depend on theta, not things that depend on xi. So you have an xy model, which is a spin-ON model in which the edges are stronger, or I mean the relationship between the edges is stronger or weaker depending on how big the norms are. So it is quite natural. The bigger the norm of the GFF are, the more difficult it is to turn a little bit, because if you turn a little bit, you will have a big distance in norm square. So essentially, the higher the GFF is, the lower the temperature is for the XY model. That's the intuition. The higher I am as a GFF, my angles, they want to move less. So it's an XY model, which is more and more frozen. And at the same time, if the norm is 0, then you don't care about the angle. So it's like you don't have that edge anymore. So an important corollary is that the spin-ON models are just GFS, as long as we condition on the probability 0 event that at each vertex, the norm of the GFF is a square root of beta. Yes. So the higher, it's like I told, the higher you are, the bigger beta is. So this is our main motivation in the story. It is to mostly trying to understand the spin-ON model, which is a hard non-Gaussian model, using a Gaussian model, and where is going to be the hard part in the conditioning. So we have to condition on something that is highly unlikely. However, okay, so the same type of result is true for the spin-ON model. So this is a fun story. If you go from the spin-ON model, you can project on, I mean, if you know the projection on one coordinate, let's say the C coordinate, you are in a sphere, then you have something that lives in Sn-2. So you take out 1. If you properly renormalize it, you also get a spin-ON model, okay? And here the temperature, how it goes, the higher you are, the closer you are to the top. Yes, the less your spin matters. Yes. So if you are close to the top, you are really hot. Actually, the angles can move a lot. Like if you are exactly in the top, it doesn't matter. If you are like really at the north, close to the North Pole, you can change angles quite easily without changing much of the distance. So near to the top, you are warm, and near to the center, you actually have the same beta. The same temperature as you had your system before. Okay. Okay. So now, okay. So here is the image of how you do that. So now I need something. So to tell, I'm going to use the first time. I'm going to use the GFF to tell you something about the spin-ON model, and it is I'm going to construct a GFF on the metric graph. This is a now classical construction done by Titus Lugo in 2015, in which you take a GFF on a graph. To each edge, you associate a Brownian bridge going from one point to the other. And the magic of this is that it still keeps the Markov property. Yeah. So somehow, if you stop in the midpoints, you still have what you have left to visit is just a Gaussian free field with those boundary conditions. And for those who have seen it, this was done by Thomas Lengler. This is the image. You have a GFF here. It's quite hard to draw it. Here in the pink one, there was an edge. Yes, and now you replace that edge by a copy of 0, 1, and you put a Brownian bridge going from that one to that one. So you get this messy type of stuff, but it allows, the cool thing is now it has the intermediate value property. So if you start from 0 and then you have a point that is bigger than 2, that there is a line that you will cross, like every path will cross at a point where it is 1, for example. You cannot go from 0 to 2 without going through 1.
These are the springs in your bedroom.
Yeah, somehow. It's like the springs. It's like one has to think that the spring is not one spring, it's many springs.
Yeah.
Close together, and you can hit those springs, and they are also moving. Yes. So it is. And one can do the same thing for the ON model. Yes, we do the same thing for the ON model. However, like the ON model naturally lives on the circle. But if you want to get the good stuff here, you need to add Brownian bridges that live on Rn, not on the circle, not on the boundary of the sphere, but if they live in the whole plane. And if you do that, well, this will still have the Markov property because it's a GFF. I mean, that's the main reason. It's just a GFF condition on something on the vertices. But the conditioning, the only thing you need to keep is the conditioning. But now you have to understand spin-ON models with different boundary conditions, like with boundary conditions that may be all of them 0, even though like all of them live in the. So this is a cool thing, and this is because we understand the GFF, we know that this holds to be true. And one can do the following percolation problem now. So we can look at, and now we are just going to care about the last coordinate of our spin-ON model. Okay, so it is the height, how close I am to the equator, or I mean either to the equator or to the poles. Okay, so I'm going to see if in an edge it didn't cross 0. Okay, so I look at every edge and I see if the last coordinate didn't cross 0. So actually it's not exactly the equator because now it's a Brownian bridge in Rn, but that if one just look at that coordinate, that's just like a Brownian bridge itself. It's no more complicated than that. And we have the following theorem. In fact, we care about this type of correlation function, like the true point. That was our main question, our main object of study, that we are trying to get to Polyakov. We are far away from it, but we are getting closer and closer. And one technique is to write it as a percolation problem. And this 2-point function is at most n, which is the ON model, times the probability that x is connected to y through this percolation. So x is connected to y by a path that does not cross 0. And 1 over n, that probability. So it's not exactly that probability, unless n is equal to 1, which is the case of the easy model. So the proof is many students here have seen it, even though. So the game is so the upper bound is if you are, so this point product is just the sum of the n coordinate plus the n minus 1 plus like the n coordinates. So we just need to upper bound the theta n times theta n, and we need to bound it by probability that x is connected to y. But when x is connected to y by a positive path, by a path which does not change zeros, then both of them are the same sign, have the same sign by continuity. It's like if I go from this one to this one and I didn't cross 0, and if I have a continuous path, then they have to have the same sign, so the product is at most 1. And that's a trick. And when they are not connected, when they are not on the same component, then I have a 0, a boundary of 0. Yeah, so I can start from x and explore every edge until I hit 0. And I haven't eaten y. And because I haven't eaten y, I can use the reflection principle. The sign of theta in y is as likely to be plus as it is to be minus. So then it doesn't matter on this side. The lower bound uses a little bit more of isomorphism of the GFF story, so I will not. One has to use an FKG property, and this is quite fun. Good. And I'm not going to prove this theorem, but I want to tell you why we care about this connectivity. It tells you that if P complement, so P complement are the points, are the edges where I am 0. Okay, so if P complement does not percolate in the dual of lambda, meaning what actually we care is like it does not make big cycles around 0. So if this is not possible, then the 2-point correlation function it is polynomial. So this is going. We are trying to recover this Patraskayu-Seiler argument, and where we say there are two options: either P complement does not percolate, meaning the points that hit 0 are not everywhere. Then we are good. So now we have to assume that. So what happens if P complement does not percolate? Okay. So if P complement does not percolate, so recall that P complement are the vertices, are the edges. So I hit 0 on the theta n hits 0 here. Yes. So essentially, what I claim is that here, if the temperature is low enough, here I should be close to the equator. It is really hard not hitting 0 if I'm not at least close to the equator, if beta is really big. Yes, because that means that somehow you started here on top, you finish here on top, and you make a big wave here. So it is quite unlikely. So one could imagine then that the set of places where I am cold, so the places where I am cold here is actually quite big. It's everywhere. I am cold everywhere except in these forbidden zones. Okay. So I claim that because if the set P complement percolates means that like I have a lot of zeros going around. So this set where I'm cold, the sets where I am either here or here should be pretty small. Agree? Like there should be small islands. They should be pretty isolated. So actually, and everywhere else, my XY model now is an XY model at low temperature. I put code here. This is this mistake. So these are the hot parts. So this is at the part where I don't want to be. Is when I'm hot, I can lose my step. But what I mean is the following. So my graph looks now like small patches, really, really small, of here the XY model is hot. So which XY model, you may ask? I start with an O3 model, also called Heisenberg model, and I look just at the projection, and I look at the XY model that is associated to that one. And I say that conditionally on the height, I have an XY model that is cold everywhere, much lower than the critical temperature, except at these even spots. But this should somehow behave like a percolation. It's like it should behave like XY model on top of a percolation cluster that is super critical. And actually, this was afterwards studied by Paul Dario and Christophe Garban, and you can show that you also have there the BKT transition. So that would mean that actually our XY model living on top of here could be should also have a correlation that decay polynomially, and we would be good. Yes. So where is the trick? Okay. So this is what we believed, and we believed this idea. So we needed to essentially start studying what was the behavior of these hot points and saying, okay, these hot points they behave not much different than percolation critical cluster, and we are good. We would disprove a really well believed conjecture. And afterwards, we realized it was Patraskayu and Seiler who made an argument which was in lines similar to what I have described. And what happens is that actually these are not that close to a percolation. in the following sense. It is actually possible, and this is what I'm going to show you, to construct a random environment for xy in which I have small patches of really warm places, and everywhere else is cold, in which I still have exponential the correlation of the temperatures of the angles. So this is what we want to do. We want to find a random environment in which the inverse temperatures, they are invariant under translation and ergodic. The places where you are cold, they are really, really small. And still, the correlation decreases exponentially. At least, okay, so there is a game with the quantifiers. You fix the beta, and then we construct the angle. So if we have to play between both games, but it is quite convincing, the object in and the main idea is the Gaussian free field again. What? Yes.
No, I'm confused by you're adding a random environment.
Yes,
Which was not in your original.
it was not in my original, but it is the same thing as the spin O3. So we are trying to understand O3, and I say that O3 is just O2 in a random environment.
Okay.
And the random environment is given by the height. And this random environment is quite weird because everywhere it's cold,
Okay.
but in these patches. And I want to say, and we would want to conclude from there. And I want to show you that that's not enough to conclude. And the main reason is because of the massive GFF. So you take a massive GFF, a massive two-dimensional GFF, actually n-dimensional works also, and you will have that the angles, because the decrease of they are exponentially decreasing in correlation, their angles are also exponentially decreasing. Actually, the level sets, which are I told you, in a GFF, the higher you are, the colder you are. So these are the warm places, these points. So these warm places, they are small enough, depending on M. For NEC, there is a mass such that the level set phi of phi is smaller than square root of C, they do not percolate for a massive GFF. That's in general, and as long as, and this will work as long as the massive GFF has dimension at least 2. Okay. I don't have much time. So the main, I'm not going to give you the main proof of this, but there is a quite proof of, so this comes from the following statement. It comes from the fact that if you start from a GFF with boundary condition 0, okay, do I have the drawing? If you start with a GFF of boundary condition 0, and you explore all the paths for which the norm is smaller than a given value, as long as you have at least 2 GFFs, one it doesn't work, but if you have 2 or more GFF, this set does not enter into the box, meaning that this distance is less than epsilon n with high probability. Okay. And how does one prove this? Well, you explore the set. You can explore it in a Markovian way. You are walking until you exit height r. You sample then the angles, and you are going to see how correlated the angles are. And we can use Melvin-Wagner's idea to show that, in fact, well, the angles, one can see that they are a long-range XY model or spin-on model, and still one can use Melvin-Wagner's argument to show that they will decorrelate, well, this time logarithmically slow. But that means that seen from the center, the harmonic function is close to 0. And for those who know about the GFF, that's the end of the proof. If you have the harmonic function is telling you a lot about how big a Markovian set is. If the harmonic function doesn't move, then this set cannot enter much. That's the method. So it's cool because it came, I mean, this is something we learn about the GFF using spin-on techniques. So we have gone both ways. However, so at least this somehow this gives you the idea of why Patraschowian-Seiler argument is flawed. But it also gives you an idea, which is quite nice, which is like, okay, let's fix the GFF. So if we wanted to prove, so here is our hope, we wanted to go and prove this Polyakov's conjecture. Okay, that's our dream. So we would at least, let's say we want to do it not for a fixed temperature, but we want to use a random environment. Okay. However, our random environment, we don't want it to have warm spots. These warm spots like somehow may break everything. They are not nice. So we are going to break them. Okay. So one way of breaking them is conditioning them. No. So I will take a GFF and conditioning, and when I will condition on no warm spots, meaning that I will condition on the norm of the GFF to be bigger than something. And then I want to study the angles. That would be my dream. So let us first do it. So this is all these drawings are done by Aleksandra. She's an amazing artist. I didn't want to put it in every line. But so here you have a big GFF, really happy, and comes and wants to not hit a really small mouse. Yes. So you want to condition a GFF so it never takes values on the ball of center 0 and radius epsilon. Okay. So it can be a one-dimensional GFF, just one GFF, but you see that it's quite understandable. We want to have 2 or 3 copies of the GFF and condition the norm to not be there because it makes more sense to us. So then there are different possibilities. So this is what we studied. And when we started, we were wondering what is the possibility. Either the GFF doesn't care. Like, okay, why would you care? There's a small mouse just running around there. Yeah. So you just ignore it. You are not paying a big price. The second one is that the GFF gets scared. So you get really scared. So you try to not be close to the mouse. So is it the GFF brave or a coward? And actually, it happens that the GFF is a coward. It happens that the GFF, if you take a typical point, let's say 0, and you condition that. So let me do the drawing to be more precise. You take the GFF and you condition it. So you have 0 here, and by technical reason, let's say that here there is for all x the norm of phi x is bigger than epsilon. So it's not that much of a thing to ask for. You know, I mean, a point typically doesn't satisfy this. This means that this is what I wrote here. So this is n/2, and this is n. So then you look at 0, and then you look at the value that 0 takes. Typically, one would expect that it's of order 0. So the GFF has a variance which is of order square root, a variance which is of order log n. So typically it's plus minus square root of log n. And the maximum of the GFF is of order 2 log n. Actually, there's a square root of g which I ignore. But Aleksandra would kill me if I don't put it there. But this is the order of the maximum, meaning that the GFF put itself in a position where it can fluctuate as almost as the maximum itself. So it really runs away from the mouse so that it can play around, and even if it really plays around close to the mouse, it will not hit it. And this we saw in a talk by Oren like 2 years ago, where he was discussing these type of things, but for a different model. So people started to study this in the 2000s, but they started to study it for just one GFF and conditioned to be strictly positive. So this is really like a big barrier, and we are here putting a small mouse, and the effect on GFF is the same. So if you put a big wall here or put just a small mouse, the GFF is as scared of both of them, and it will always run so that the norm is 2/square g log. But we care more about the angles. Yes, so we care more about how far the GFF is. And there are 3 options for the angles. So the first one is what is drawn here, at least, is that the GFF chooses one angle. Yes, so it chooses like a whole angle, and it goes in that angle. So it is that the norm is 2 log n, and it chooses an angle. The second one is it doesn't care. So it's like it has one part like to this side, the other part to that side, but it doesn't matter, the angles are not that important. And the third one, which Aleksandra had drawn, but I couldn't find, it is that it's actually like quite uniform. It doesn't care about the angle, it's uniform on the angle. And what we could prove with Aleksandra is that in fact the angles freeze, meaning that almost every angle. Okay, so we have a stupid thing. So I'm the only thing we could prove essentially, but it is, or we were almost there, is that at 2 points that are at distance n to the 1 minus delta. So we couldn't go all the way to macroscopic, but all the way to mesoscopic, angles freeze each other. Okay, and we have to have a typical point story which says like almost every deterministic angles, almost every deterministic point satisfies this. The density of the ones that do. It just simplifies the proof, but it shouldn't matter. Like all the angles should look at the same side. And with this, we realize that this is not the good model for what we were asking. Okay, so it's a little bit sad, but it's not the good model because, I mean, you will not have exponential decrease of the correlation. You are frozen. Okay, it's completely the opposite. But we already know how to fix it. We have to fatten the GFF. Yes, so you have to put some mass on the GFF. Because when you put mass on the GFF cannot run anymore. It's just too costly. And we could prove this with Aleksandra. And this is the last result I will present, but it's essentially saying that, well, if you condition a massive GFF now, not to hit a ball of any radius, still the GFF is tight, meaning at least that the expected value of the conditional norm is less than infinity. It cannot escape because it makes too much effort running. So why would you run? And you stay at similar distance. And the future now, what we would expect here is that we can work with this model. So we take the conditional GFF, we take the boundary to infinity, okay? And now we start studying this object, the angles of this object. And because it's massive, we can expect that sometimes, at least for big N, there is an exponential decrease of the correlation. And if there is an exponential decrease of the correlations on the angles, we are getting closer to Polyakov, because we have now it is a GFF with no, it is an XY, a spin-ON model with no warm spots. So what we are missing for that is a monotonicity afterwards. Like the colder you are, the more aligned you are, which somehow it's intuitive, but that's we would need also that to conclude Polyakov. We know what happens to the angles in dimension 1 of the massive GFF, and they undergo a phase transition as the XY, as the Ising model. If you take a massive GFF and you look at either it is positive or negative, if the epsilon is small enough, well, the massive GFFs can cross over the mouse, and you get, like the Ising model, just one infinite volume limit, for example, or you have. However, if you are cold enough, meaning that the mouse is a really big mouse, yes, so you cannot, your flattened GFF cannot jump over it, then you will get low temperature. So meaning that the 2-point correlation function, your GFF is either going to almost all of them be positive, or almost all of them be negative. Yes, so that's the story. And well, thank you.
No, you believe that the Polyakov conjecture is?
Yeah, sadly. I was so happy when we realized about this argument. It felt like it was going to be true. It's like a lot of
false.
Huh?
You felt it was going to?
Yeah, I felt it was going to be false. So I believe in this argument really a lot until I realized that the spins of the massive GFF do not work. Then I had certain hope that the massive GFF, the level lines of the massive GFF, like the price where you are 0, they are at the level lines of the one-dimensional GFF, meaning that they percolate or almost percolate. You make big loops. And then this was for a moment the understanding, and then we realized this is not the case. So it was somehow a little bit disappointing. And at the same time, there is another good reason, is that actually the model of randomness for XY being a GFF is not, like a massive GFF, is not a bad idea, in the sense that if you look at the random environment generated by a spin-on model, where you fix, let's say, the 0 to be completely north. So you are here on top. You take beta, go to I always confuse. Beta goes to infinity, so you get really cold. Okay, this is really close to a GFF. So we also show this. This is the good environment. So the E environment also looks like a GFF, at least when the temperature is 0. So you imagine when you put a little bit temperature, it should look close to that of a massive GFF. And if it looks close to that of a massive GFF, you know exponential decrease on correlation. So it is so essentially, through the path of trying to disprove it, we found a lot of evidence that it should be true. And the strongest one is the angles of the massive GFF, because the GFF is somehow embedded also as a limit of low temperature on the spin-on model. However, there is something funny, because the arguments, they cannot work for 2-dimensional GFF, but they should work for 3. So there is something really, really beautiful over there that we still don't manage. There is a nice story of, essentially, it has to do with the percolation. So, like, I introduced this percolation structure in dimension, where essentially you look at the percolation, look from a certain projection. Okay, so if you are in dimension 2, you have 2 percolations living together, one for the first coordinate and one for the second coordinate. Okay, and they can only hit each other in a way, in points where you are warm, and then it's hot. But in dimension 3, somehow you have, it's like you have a highway system with a small how it's called, like rotondas,
Roundabouts.
with small roundabouts, but these allow you to connect everyone. Like because in a way it's like 2 percolations that cannot hit each other except in really small points. And somehow, okay, in my mind that makes sense that it works in dimension 3. It makes more of these points. What I didn't tell, however, is that the physicist intuition is completely on another way. It has to do with the symmetry group of these objects. It's like the symmetry group of y is commutative, well, almost commutative. I mean, it's okay. It's commutative. You always have. It's completely commutative, and the one of O3 is not. Like you have, but we still don't understand why commutativity should play a role, but they are completely sure of it, so it should be true.
Questions on Zoom?
No question in the chat.
Okay. Okay, so I think
You are invited to come with us to celebrate the last